National Heritage. Chris Aris is based at Weale University. Sarah Reearch is also independent, but she's previously done the Masters at UCM. And Alison Fox works for Maternal Health. We are also being funded by Culture Banning, very generously, and we're very grateful. So first of all, my presentation contains topics that might be quite triggering to people. So if at any point you feel a little bit uncomfortable, you're more than welcome to leave. Also, if you find me quite boring, you're also quite welcome to leave. Yeah, it's just one of those things. It's a controversial topic. Some people might find it a little bit too much, and it's absolutely okay. So, first of all, maternal infant dyad. So when women are pregnant, maternal health is really important, which obviously we would probably all know. But what that woman endures during that pregnancy and what she's exposed to has a long-term effect on the health of that child throughout their life. Maternal health is the foundation of every population. The healthier your mothers are, the healthier your children will be, the healthier your next generation will be. So when we're looking at this, we're looking at intergenerational effects. So when a woman is pregnant, if she's pregnant with a girl, the eggs form in utero. They mature later in life, but they form in utero. So if that mother is exposed to an adverse environment during her pregnancy, not only is her child affected, but the next generation will also be affected. And you see evidence of this in some of the kind of awful things that happened during World War II. So when you look at things like the Dutch Hungry Winter, pregnant women were allowed a ration of roughly 800 calories a day. The siege of Leningrad, the Holocaust. Those effects of those awful things are still being felt 3 generations down the line. So, and it's all because during development, embryos and fetuses are influenced by adverse phenomena. And there's a thing called fetal programming. And what it does is it makes sure that the baby will survive. And it's almost like a trade-off. So the baby will be born with a respiratory system and a brain that it would need, and the body would prioritise that. But other organs, maybe the heart, maybe the kidneys, are not as developed as they should be because the body had to prioritise certain organs as it had certain resources. And it's all very interesting, and you can go on and on about it forever. So I'm quite a theoretical person, and life course theory is something that really interests me. Because all societies are shaped and moulded by biological outcomes, strategies, and to investigate them we need multidisciplinary approaches. We can't study one thing without looking at everything that's influenced by it, if that makes sense. And that's kind of what the theory allows for. So when we're looking at the life course approach, we identify that individuals actually transition. So these babies that are born become young children, they become adolescents, they become adults. And their social status might change during that time. Their age is definitely changing. Biological sex does remain the same, but it is a factor on how these things can work. So it seems a bit hard to talk about life course theory in populations where the people didn't survive. And there's a big thing known as the osteological paradox, which is that all archaeological samples to some extent are limited because they're made with people who didn't survive. Seems logical, but actually there's a mixture. So within any archaeological population there's usually fetal or neonatal individuals, there's young children, adolescents, and adults. So we capture the whole kind of circle of that population within our sample. But also, what we can do is, what we look at really, is the children. Children are much more susceptible to things within a population than adults are. They're not as resilient, their immune systems haven't formed properly. But also, they don't care for themselves. They're dependent upon the people of the population. So if the children are sick, then something is going on somewhere that potentially we're not able to see. So how do we study maternal health in the past? So 2 things. So human skeletal remains and teeth. So skeletal remains, we can look for things like growth. We can look for diseases, so nutritional diseases diseases and also hereditary conditions that can be passed from one generation to the next. But teeth are the big thing, because bone changes. So your bone is an organ, and it changes and it remodels as you grow. So some diseases, vitamin D deficiency, vitamin C deficiency, if you're only deficient for a short period of time, then that deficiency is regulated again, that evidence is removed from the skeleton. So it's kind of a snapshot in time, if that makes sense. Whereas teeth don't change. So adult teeth, or certain adult teeth, actually start to form in utero and capture the whole of childhood. So actually they're amazing markers to study childhood health, and they don't change. So once your tooth mineralizes and then starts to form, it's a kind of chronological record, and you can actually age episodes of deficiency within the tooth, which is also pretty cool. So I took samples, so it's quite a small study. Initially, we were like, right, we're going to get 25 teeth, and this is going to be amazing, and then preservation was rubbish. So if there's anybody in here who's like, research is amazing, like you're going to do exactly what you want to do, you're not, okay? Like, no research ever goes to plan, and you have to adapt and change with how your research works. And I think that's something really important to highlight. So instead of 25 amazing dental samples, we have 11. But you know what? It's better than none. So we have one from Peel Castle, but we have no skeletons from Peel Castle because the soil environment is just not great for skeletal preservation. We have 2 teeth and 2 skeletal samples from Ballador. We have 6 teeth and 2 skeletal samples from Russian Abbey. And then we have 2 teeth and 2 skeletal samples from Cronk-Clay. So when I say skeletal samples, I mean neonatal individuals. So again, at this point I'm not looking at the adult skeletons just yet. We're looking at the neonatal skeletons to really kind of home in on what's going on. So this is an individual from Russian Abbey. There were 2 individuals, 2 neonatal individuals found. One was approximately 31 to 33 weeks, and the other was 33 to 35 weeks. But these are, 35 to 37 weeks. But these are based on modern age estimation standards. So the children path would have been smaller. So we have to allow for some leeway on the age estimation. But what I can tell you is they were newborn or very much around that time. But they weren't very healthy. So this is, I've got the name of that bone, so we'll come back to that one in a second. These are skull fragments, and if you can kind of see here, there's like little, almost like porous areas, and this is evidence of increased vascularity in these areas, so increased blood flow, right on the top and the soft spots all around the head. Okay. This is the mandible, and what you can see is these lines running down here. So this is evidence of the muscle attachment. So as this baby was sucking its thumb, which it can do in utero and after birth, the muscles were moving, and those muscles were hemorrhaging because they didn't have enough vitamin C deficiency, and it was bleeding. And that's what's caused the porosity and the new bone formation in this area. And this is what you see in individuals who have vitamin C deficiency. So this individual had scurvy. When we look at the ribs, so this flaring and this porosity that you see here, so this is a growth site that's really important in the development of the ribs. And you see porosity and you see flaring. And this is something that you would see in individuals that had vitamin D deficiency, so rickets. And when you look at this bone, sphenoid, there we go, sphenoid. It sits behind your eyes. So it is, your eyes actually, the bone at the back of your eyes is actually part of it. It's a huge structure and it looks almost like a big bat. But this is the body. And here is what they call, it's a feature called the sella turcica, which is literally Latin for Turkish saddle. Apparently it looks like a horse riding saddle. And that is where your pituitary gland sits. So that's where the hormone gland sits at the bottom of the brain, if anybody in here is a biologist. But it's also where really key areas of the brain connects and all, things attach and flow. And again, huge amounts of vascular, like just bone porosity, huge amounts of new bone growth, so really, really advanced vitamin C deficiency in this individual. The other individual also showed similar types of characteristics. The other individuals from the other sites didn't show vitamin C deficiency, but they showed evidence of vitamin D deficiency. But we live at 55, 56 degrees north of the hemisphere. We spend approximately 6 to 8 months of the year without adequate vitamin D deficiency, or without adequate sun to synthesize vitamin D. So, okay, it would make sense. But to have this amount in such a short time, the mother was deficient, and it was passed from mother to child. And the neonatal skeletons that I'm looking at are the individuals who didn't survive. Okay? And it sounds awful, but it is the truth. But the teeth show a slightly different process, because the teeth were able to mineralize and were able to form, and they're evidence of the individuals who did survive. Of the named population, you have evidence of the individuals who didn't, and the evidence of the individuals who did. So it's good to look at both, because sometimes it's just a genetic lottery. Some people survive and others don't. But are all individuals who suffer this dying really young? Can we see evidence of it later in life? Do we see individuals who survived and then went on to grow to adults? And these are all things you have to look at when you're looking at the dynamics of the population. So the dental histology is still underway. But I wanted to kind of come today and kind of show you the process of the research and how it works. So first of all, if you're going to do a study like this with lab costs, you apply for funding, and you apply to like 2 or 3 different organisations maybe, and if you're lucky, they like you and they'll give you some. At that point, then you select your samples. So like I said, originally we had 25, and then that didn't work out, so we got 11, but again, it's still good. Even after I select the samples, I have to apply for permission to do destructive analysis to Max Natural Heritage. And I have to write an application, I have to detail out exactly what I'm going to do, how I'm going to do it, why I'm going to do it, and what is the justification for it. And at that point, they could say no. Thankfully, at this time they didn't, and it was okay. But even then, you also have to get a license and all this other stuff to be able to take archaeological material off island. So at that point, the samples were then taken to Weale University. They went at the start of September, and they're currently undergoing micro-CT. So does anybody ever have a CT scan? Yeah? So same idea, but super small. So what it's looking at is density. And certain areas of the tooth don't mineralize correctly, which we'll see in a second, when somebody has vitamin D deficiency. So what we're doing is screening the teeth. Now, I'm somebody of the opinion, and I do a lot of destructive analysis within my work, but just because I can, it doesn't mean that I should. Okay? So, because I am destroying an artifact and also a person who could not consent to be part of my research, when we think about modern research and how we would give